We are actually in an extraordinarily cold period. We are in an ice age today. We're in a relatively warm period of an extremely cold period. And it turns out that that just lines up with the relative cold and hot in the climate. This is more of the data that I took. And so there's the 100,000 year. This is hot, this is cold, this is right now. This is roughly 100,000 years ago. That's the previous interglacial. This is the eccentricity cycle, 100,000 years. There's the precession cycle, 23,000 years. That's the tilt cycle, 41,000 years. It lines up. These orbital changes absolutely dominated our climate for the last 500,000 years. All that is driven by orbital changes. So the nice thing is, though, that you can calculate how these orbits are going to affect climates, because this is what absolutely has dominated our climate for the last 500,000 years. And we should be able to figure out what the climate should be doing given the solar input. And 10,000 years ago, it was really warm. This is the line you need to look at here, because this is summer insolation, the amount of sunlight you're getting at 65 degrees north. And it peaked about 10,000 years ago, and then has been in decline ever since. So what should be happening is we should be dropping into the next ice age. Climate should be deteriorating. Things should be getting colder. So I'm going to show you a bunch of stuff. The problem is with climate, there's a lot of things going on. This is not soundbite science. But with climate, you hear a lot of stuff. You see greenhouse gases are warming the globe. Sunspots actually cause the warming. These are actually the sunspots from Tuesday. That we're in ice age. That the glaciers are melting. Sea level is rising. CO2 is natural. CO2 was a lot higher in the past. CO2 was a lot lower in the past. That the Earth is a lot warmer in the past. The Earth was a lot colder in the past. And the problem is that everything here is true. Sound confusing? Well, no, it's not. Actually, it's quite reasonable. The thing is, we actually know quite a bit about past climates. But what this does is it tells us we know the Earth's climate history pretty damn well for the last 500 million years. After that it gets a little tricky. And so we can actually look at what's normal for Earth. And the question is, what is normal for Earth? Is today's climate normal for Earth? And so what's normal for climate? This is Phanerozoic. Phanerozoic is what you live in today. That's the period when you have like complex critters. We are here at 0 in the Neogene. Go back a 500 million years. And the first thing you see is that it is about as cold right now as it has ever been in the last 500 million years. We are actually in an extraordinarily cold period. We are in an ice age today. We're in a relatively warm period of an extremely cold period. I didn't say this was going to be easy. This is, reality is just, I'm not going to sugarcoat reality. This is reality. And so we are very cold. Back during the Cretaceous, the K means Cretaceous. Scientists don't spell well. It was extremely hot. But average for Earth is a lot hotter than it is today. But what you should take away from this slide is there's nothing normal about climate. Climate varies a lot. And it varies a lot for very good reasons, which we can figure out, and which we will figure out tonight. But what were things like in the Cretaceous? Cretaceous with a C. Back in the mid-Cretaceous, this is the temperature profile by latitude. We are about right there, about 30 degrees. So actually, the climate for the latitude of Pensacola was not all that much different in the Cretaceous than it is right now. It's pretty warm. Not unbearably warm, because with a little bit of air conditioning, it's very pleasant to live in Pensacola. But it's much different than the present day. And the difference is not in the low latitudes, it's in the high latitudes. Because in the Cretaceous, nowhere on Earth, even at the poles, was it on average below freezing, if you can imagine that. In the Cretaceous, you had a temperature profile that essentially made what you consider temperate climates going all the way to the Arctic Circle. You had tropical conditions to 40 degrees north-south latitude. So that's the same latitude as New York. Can you imagine the climate of Key West in New York City? Why so much warmer? Well, back then, CO2 was about 1,700 parts per million. Anyway, so why so much much higher CO2, a much different ocean circulation in continental locations, but there was a downside to all of this. So basically, this would be, in the Cretaceous versus now, this would be the same location. This kind of vegetation, which today it looks like that. The downside, of course, is that no continental glaciation means a much higher sea level, something like 150 to 200 meters higher sea level. Now you ask, well, is that normal? Well, what is normal sea level? We are here at 0. So you see the spikiness here? That's actually real. Sea level is actually highly variable, and not just from melting glaciers. It turns out that the mid-ocean ridges, where most of the volcanism occurs, this plate tectonic stuff, the plates actually move around, they actually vary quite a bit. And when the mid-ocean ridges decide to crank up and expand and create plate faster, they actually expand. If they expand, there's no other place for the water to go except into your homes and gardens. So let's talk about the recent climate. And the recent climate is like the last 50 million years or so. Back in the Eocene, it was pretty warm. And then what's been happening over the last 50 million years is a slow deterioration, but steady deterioration of the climate. You actually didn't get Antarctic glaciation until about 35 million years ago. And then it glaciated and thawed out and reglaciated. And since it's been reglaciated over the last about 12 million years, there's been this very steady, very sharp drop in the average temperature of the globe. Why is this happening? If you just look at the last 5 million years, this trend has continued and it's been very steady. And what happens is that it's climaxed in a series of glaciations. In the last million years, these glaciations have greatly intensified. And so you're getting bigger swings in climate as it gets colder. And so what we're living in is a relatively warm period of what is an incredibly cold period in Earth history. So this is the last 400,000 years, and I actually took some of this data. We're here. And what you find is for the last 400,000 years, there have only been 4 periods when it was this warm. And these periods usually last 3,000 or 4,000 years. Does that make you worried? It made me worried.
Is that the climate has constantly oscillated back and forth. And when we look at the Holocene, going back 10,000 years, and then we take that comparatively and we go back 250 to 400,000 years, we can now begin to reconstruct these intervals of glacial periods, interglacial. And here's the thing that should be sobering to everybody on the planet today as we think about climate change and all of this, because obviously it's constantly in the news and all. The longest interglacial period now on record for at least the last 250,000 years, the longest one, the longest unbroken period of interglacial warmth is the Holocene, the one we're in now. We've already exceeded by several millennia the longest previous period of interglacial warmth. I don't hear him talking about that. I don't hear Al Gore talking about that. I don't hear anybody talking about that in mainstream media, but it's hard scientific fact.
Yeah, we would be in our pants way more if it was a global cooling.
But anyway, we're here, and we're actually in the most extraordinary long interglacial. The warm periods are called interglacials. And these things are typical. The glacial periods are characterized by this stepwise deterioration in climate down to a glacial maximum. Now, what are glacial maximums like? The last glacial maximum was 18,000 years ago. So what caused the ice age? Well, blame China and India. And what happened is, over the last 20 to 30 million years, India collided with China and created the Tibetan Plateau, an extraordinarily high set of mountains. That really, when you raise stuff up like that and you break up rock like that, what you do is you vastly increase rock weathering. Now, I can go into excruciating detail again on the chemistry of rock weathering, but the bottom line is that it sucks carbon out of the atmosphere like crazy. And that's what happened here. We've lost about 80% of the carbon that was in the Cretaceous atmosphere due to the Himalayan rock weathering. And what happened was, this has basically made the climate vulnerable to small changes in solar energy inputs. Now, and these small changes are caused by orbital variations. The orbital variations are always there. But since you don't have as much greenhouse gas in the atmosphere, it makes it more difficult to distribute heat across the planet. And if you don't have the greenhouse gases, you're not going to distribute the heat into the polar regions. And if you drop the solar input to the polar regions, you're going to end up getting glaciers. And so what happens is that the glaciers are triggered by variations in the Earth's orbit. The way this works is, blame Kepler and Galileo and Copernicus. The Earth's orbit is not a perfect circle. You actually are closer to the sun by about 5 million kilometers in the middle of winter. And it's really easy to remember. Aphelion is July 4th. Everybody celebrates aphelion. Nobody celebrates perihelion. I could never understand that. But you get 6% less solar energy at aphelion. And aphelion happens to be in the summer. So this actually moves around in the orbit and in the seasons. It's called precession. And so right now, summers are a little bit cooler and warmer, and winters are a little bit warmer because of the positions in orbits. But that changes over time. And it can be a fair amount. 6% of solar energy is a fair amount. This is basically a simple idea. If you have warm winters, you're going to melt all the snow that falls in your really cold. If you have warm summers, you melt all the snow that falls in your really cold winters. If you have cold summers, that can allow snow to accumulate in the right latitude range. And also, warmer winters tend to produce more snow. And I think we're starting to experience, last year was a good example of that in the Northeast, where it was relatively warm, but it was really, really snowy. The guy who puzzled this all out was a Serbian mathematics professor called Milenkovic. The question is why there were ice ages. Because you could see abundant geologic evidence that there were at least 4 big ice ages, 4 big glaciations in Europe and North America. And the burning question was why? And he went back and he actually was able to publish in 1925. And what he found was that if you look at these cycles, that the orbit of the Earth's orbit actually affects the amount of sunlight you get tremendously, because there's an eccentricity cycle that goes from about 0 to 6 degrees in the roundness of the orbit. There's a tilt cycle that goes from about 24 to 21.5 degrees, and an index of precision, that where you are in the orbit when you're closest and farthest from the sun. And you can combine all these effects and actually see how much sunlight you get at high latitudes. And it turns out that just lines up with the relative cold and hot in the climate. This is more of the data that I took. And so there's the 100,000 year, this is hot, this is cold, this is right now, this is roughly 100,000 years ago. That's the previous interglacial. This is the eccentricity cycle, 100,000 years. There's the precession cycle, 23,000 years. That's the tilt cycle, 41,000 years. It lines up. These orbital changes absolutely dominated our climate for the last 500,000 years. And all the other things that you hear about in climate, El Niños, Pacific oscillations, Atlantic decadal oscillations, all these are in the noise. All of that is subsumed in the thickness of the lines you see here, because this absolutely dominates. This is what creates a mile-thick glacier on top of New York City. And just because it's a little rainier because of El Nino, that's in the noise compared to having a mile-thick glacier on top of your apartment. Okay? So that's where we are. So our climate for the last 1,000,000 years has been characterized by these long periods of terrible glacial conditions. Glacial conditions like, tundra in southern France. All that is driven by orbital changes. So the nice thing is, though, that you can calculate how these orbits are going to affect climates, because this is what absolutely has dominated our climate for the last 500,000 years. And we should be able to figure out what the climate should be doing given the solar input. And 10,000 years ago, it was really warm. This is the line you need to look at here, because this is summer insolation, the amount of sunlight you're getting at 65 degrees north. And it peaked about 10,000 years ago, and then has been in decline ever since. So what should be happening is we should be dropping into the next ice age. Climate should be deteriorating. Things should be getting colder, given the solar input. The problem is that it hasn't been. Solar input is dropping, but the ice is melting. So what's going on? And what's going on is us and greenhouse gases, CO2 and methane. What happened is that our ancestors were smart kids. Up until about 8,000 years ago, the atmosphere stuck with historic trends. But about 8,000 years ago, our ancestors invented agriculture, started clearing forests. When you clear a forest, what you do is it's slash and burn. You put lots of carbon back in the atmosphere. You control the forests with fire. Very intensive, very carbon-intensive sorts of agriculture. Methane the same way. About 5,000 years ago, they invented rice cultivation and domesticated livestock. Nothing is a better methane producer than a herd of beef cattle. And so human input to the atmosphere started a long time ago. It's not just us in the industrial age. Basically, in the pre-industrial age, you started out with about 260 parts per million CO2. And human activity stopped the decline of CO2 and methane in the atmosphere and cranked it up to about 280 parts per million, essentially putting carbon, gigatons, billions of tons, a gigaton is a billion tons, of carbon into the atmosphere. So about 80 gigatons of carbon. That's equivalent to about 10% of the biomass. But that's about right for the forest clearing that happened in the pre-industrial age. The problem is that your solar input is still dropping. And so even though you're tossing in more carbon from burning more forests and domesticating more livestock and making more rice paddies, there's a point of diminishing returns. And so actually things started to get colder back in the Middle Ages, simply because you couldn't keep up.
Well, a lot of those Gothic cathedrals were never finished. And what we see is that some of them have the appearance, I'm a builder by profession, and I've looked at some of these, and what it's very much like is they're going along building, and then all of a sudden one day nobody shows up to work. And there's still tools laying around, there's still materials that are off in a pile that were waiting to be incorporated into the structure. And what happened was that the climate began to cool again between 1315 and 1320. Precisely when we see the end of this tremendous Gothic building boom is when the climate began to cool. And it cooled for the next several decades. And what we then see is a repeat of what happened between 536 and 542 AD. Agricultural collapses, crops rotting in the fields, people going hungry. I think it was around between 1340 and 1345, the onset of the Black Plague.
What we did then was we tapped a new reservoir. We figured out how to get into fossil fuels and use those. The whole pre-industrial atmosphere had about 600 gigatons of carbon in it. What we do now is we add about 9 gigatons a year from almost all from fossil fuels. There's a tiny little bit. This is cement production right here. All the rest of this is fossil fuels. Let's pretend, and I don't like to do climate modeling because that's really complicated. I like this model because it's fairly simple. And I'll just show you this to show that it's possible to explain short-term variation. Let's pretend that short-term climate is driven by 4 things. The sunspot cycle, because sunspots do affect solar irradiance and the amount of watts per square meter that the sun dumps on the Earth. So you get an 11-year cycle where you get a little more irradiance and a little less. And it affects it on the order of less than 1/10 of a degree C, like 1/2 of a degree C. Then you get volcanic aerosols. Mount Pinatubo blew up and threw a lot of gunk into the upper atmosphere. And that actually cooled things down quite a bit. That's Mount Pinatubo right there. And then you get the El Nino Southern Oscillation. El Nino actually does change the energy balance because it's a big lump of warm water that sloshes around the Pacific in the simplest sense. And once again, we can do this more complicated. But if you sum all of these things and say that's what drives the short-term climate with this anthropogenic influence, that is, dumping more carbon in the atmosphere, you can actually model. The black line is the instrumental surface temperature record, or as I like to call it, reality. You can actually model reality pretty damn well. Not bad, though. Fit is 87. The thing is, though, that we're just coming out of a very low sunspot cycle. Actually, historically, in the last 50 or 60 years, a historically low sunspot cycle. So things were actually slightly cooler because of low sunspots. But we're going into solar maximum right now. So sunspot cycle is cranking up. As a result, what's going to happen, I will predict, is for the next 4 or 5 years, you're going to have a succession of extremely hot years. Sad but true. And so far, it's proven, the average temperature records have been proven that that's what's happening. The point is that you can look at a glacial mass balance and it's just dropping off a cliff. Trends. I was born in 1950. When I first drew breath, the CO2 level was 310 parts per million. In this room today, it is about 390 parts per million.
You know, putting this into context, we have to say right now we're approaching 400 parts per million of the ambient amount of CO2 in the atmosphere. At the beginning of the Industrial Revolution, it was about 100 parts per million less. You could say basically that over the last century, we have increased the amount of CO2, measurable CO2 into the atmosphere, assuming that it's all from us now. I mean, there's questions about that too, because if there are other factors inducing global warming, such as changes in solar irradiance, the amount of insulation penetrating the atmosphere and so on, it means that the oceans are warming as a result of that, okay? Oceans are a gigantic carbon dioxide sink. When they're warm, they exude carbon dioxide. When they're cold, they absorb it, right? So if you have a natural warming, it's going to expel some carbon dioxide. So it's not even clear necessarily that 100 parts per million is totally the result of fossil fuel burning. But for the sake of argument, let's say that it is, okay? 100 parts per million. That's a minuscule trace of this very important constituents of our atmosphere. You know that carbon dioxide is what fuels photosynthesis, right? And if you start reducing the amount of carbon dioxide in the atmosphere, and once you start dropping below 200 parts per million, and you get down to about 150 to 100, plant photosynthesis starts shutting down. I mean, it's kind of like the amount of CO2 in the atmosphere right now is at the very bottom of the scale. You know, if we look at history going back when you mentioned the Cretaceous Tertiary, when the dinosaurs ruled, there have been many times more the amount of CO2, up to well in excess of 1,000 parts per million, several thousand parts per million in the atmosphere. But if we have increased the amount of CO2 by 100 parts per million in 100 years, it means for every million molecules of air up there, we add 1 molecule of CO2 every year. Or to maybe try to make it a little bit more comprehensible, if for every 100,000 molecules of air up there, every 10 years we add 1 molecule of CO2. I'm not convinced that that's going to lead to global catastrophe. I mean, think of it this way. You got a huge tank with 100,000 fish in it. Every 10 years you throw in 1 more fish. Are you even going to notice that? You know, I think that what's happened is that CO2, like I said, is one variable in a very complex equation. But all of the other variables, as far as the government-funded research goes, have been excluded from the debate. And what dismays me is that we're told that all scientists agree on this. No, all scientists don't agree. When you have, though, a major government-funded program like climate change research, which is funded to the tune of about $2 billion per year, you're going to have a large vested interest in basically, I mean, if these guys came out and said, nah, CO2 is really not a big deal. It's perhaps fueling plant growth. And this is an interesting aside. You know, if you look at the projections of forest inventory back in the 50s and 60s based upon deforestation as a result of timber, as a result of agriculture, the projections at how quickly forest inventories were going to rebound. If you look at those projections back in the 50s and 60s, and then you realize that in the ensuing period of time, we've now got exhaustive, highly accurate satellite surveys that can actually count the number of hectares of forests. What's interesting is in the 90s, when they really started looking at this data of just how much forest there was compared to what the projections were, there was like 25 to 40% more forests worldwide than anybody had predicted. What fueled this prolific forest growth? Well, it's very likely that at least part of it was because of the slight increase in CO2.
Okay, so some answers. Yes, we're in an ice age. If you look back over the last 500 million years, continental glaciation is very unusual. Very unusual. Does the climate vary? Of course it varies. It varies constantly. Is the current climate normal? No, normal for Miami is to be under 80 meters of water. Normal is not to have a Florida. Is the planet warming because of human action? As a scientist, I am just floored that this is a political thing for political discussion. Of course it's warming. We are well into the next Milankovitch cycle. We should be getting advances in glaciation. And we're not, because we've been smart enough to, this is called geoengineering, we've been smart enough to change the atmospheric chemistry and redistribute the heat into the high northern latitudes and make up for this solar insulation that we're not getting. Human action over my lifetime has increased atmospheric CO2 by 25% and stopped the Milankovitch cycle in its tracks. But we have to recognize what we're doing. The downside of this is that if you look in Earth history and you have high levels of CO2, high levels of greenhouse gases, you don't have continental glaciation. If you don't have continental glaciation, you don't have Miami. So the bottom line here is, do you like sea level where it is? Yes or no? Just to give you a little bit of perspective, we're here. So, 1 meter is no big deal. 2 meters, not so good for the Keys. But then again, you can see why the Florida Chamber of Commerce hates this. Ask yourself what percentage of the assessed valuation of Florida is within 10 feet of sea level.